Hello and welcome to our viewers all over the world. Today's lecture is on ultrasonic testing of welds, and welding inspection is very common in ultrasonic testing. It's done on different components, which are piping is very common, pressure vessel, structural. So the first step would be to know what code would you be following. If it is pressure vessels, it'll be ASME section 8. If it is piping, it will be B311 or B313, or if it's offshore, it's going to be OSF 101. And if it's structural, it'll be AWS D1.1. So we will now start with the lecture. And so here is the title of today's talk: Angle Beam Ultrasonic Testing of Welds. Applications, as I discussed, are piping, pressure vessels, and structural. What are we looking for? When we do the weld inspection, we are looking for common welding defects, and these include slag porosity inside the weld, cracks that can be at the ID near the root or the OD at the toe of the weld cap, and incomplete fusion between the bevel and the weld, and it's also called lack of fusion. Here is the way angle beam inspection is done. It's done using ultrasonic shear waves, and we use a probe with a certain refracted angle. In this case, I'm showing an angle of 60 degrees, and knowing the angle and the sound path to the reflector, we can actually calculate the location of this reflector, which is the distance from the exit point of the probe to the reflector and the depth from the surface to the reflector. So knowing the PA and the DA, we can actually place the reflector in the body of the component. So these calculations are done by a simple trigonometry, and which is PA equals to the sound path times sine of the angle, and the depth equals to sound path SA times the cosine of the refracted angle, and this is going to be half. For 60 degrees, it will be 0.5 of SA. So this is a direct reflection, but in ultrasonic testing, we do what's called the first leg and the second leg. So this is first leg, and in the second leg, the sound actually hits the bottom, which is the ID of the pipe or the pressure vessel, and it reflects back here, and then it goes to the reflector and comes back to the probe. So in this case, the UT machine really doesn't know where there is a reflection here. So it will actually compute the SA and the DA here at this location, which is actually like hanging in the air. So what we do is we actually tell the machine what is the thickness of this pipe, so that it automatically takes that into account and places the reflector inside the volume of that component. So here is the formulas here. PA is the same, but DA actually becomes 2T times DA dash, which is right here. So then it places it right inside the pipe thickness. So the concept of inspection is here. Inspection is done by angle beam shear waves to inspect under the weld cap, and this is called the first leg, and this is called the second leg. So here we are doing the inspection in the second leg to look for the lack of fusion between the bevel and the weld, which is right here. So again, knowing the refracted angle and the sound path, the machines actually calculate the PA and DA. Now, once we actually include this X distance, the distance from the exit point to the front of the wedge, then the machine will calculate RA and DA. So knowing the RA and the DA, we can actually place the reflector inside the weld area here. So that's how the inspection is done. Now, the older machines which used oscilloscopes, all of these trigonometric calculations had to be done manually, but in all the new digital machines, these computations are done in the machine. All we have to do is we have to input the refracted angle, we have to input the thickness of the component, and we have to add this x distance, which is from the exit point to the front of the wedge, and then the machine will display RA, which is from here to there, and DA, which is from there to there. And then knowing that, we can actually plot the reflector location inside the weld. So it's very important before we do the inspection that we know the configuration of the weld. We should know the exact thickness of the component we are inspecting. If we do not know the thickness, then it will not place the flaw correctly inside the weld, and that will lead to misinterpretation of the flaw. So the steps for this inspection are as follows, and we should know the weld thickness. We should, after that, based on the thickness, we select the probe, then we do the range calibration, then we do the sensitivity calibration and set up the distance amplitude correction curve, conduct the scan, locate the defect or the discontinuity and measure it, which means measure the amplitude relative to the DAC and apply the acceptance criteria. So now steps 1 and 2, thickness and probe selection. So depending on the thickness, we will select the probe. Normally probes are 4 megahertz, 5 megahertz, and the common angles which are used for angle beam testing are 45, 60, and 70 degrees. Now, this slide is very important. Probe diameter to depend on the part thickness and expected sound path. So here is an example showing inspection of a half-inch thick weld, and in this case we are using a 60-degree angle, 60-degree refracted angle. So you can see that with using this angle we are illuminating the root in the first leg. This is called the first leg, and it shows up on the screen here because it's half-inch thick. The sound path is going to be double of half-inch, and it will be slightly more than 1 inch because that's double of half-inch is 1 inch, and the root is a little bit deeper, so it will be a little bit here. So now what I'm trying to explain in this slide is that this angle 60 works very good for half-inch to 1 inch. As the plate or the pipe gets thinner, let's say the thickness is like 3/8 of an inch, then we will not be able to see the root in the first leg. So in that case, what we will do is we would have to go to a 70 degrees so that we can see the root in the first leg. On the other hand, if the thickness becomes very heavy, for example, if the thickness is 2 inches, then 60 degree may not be the correct angle, because with 60, even though 60 degree will see the root of the weld, but what will happen is that the sound path will become very long. So, and because of the longer sound path, the beam spread will be very high, and that will result in a reduction in the signal to noise ratio. So for that case, we would have no choice but to go to 45 degrees. So the selection of the probe is not straightforward. It depends on the thickness, and based on the thickness we select the refracted angle, and then we also want to keep the sound path to minimum so as to control the beam spread. Another point I have to discuss is that when we do this weld inspections, we should try to do all the inspection in the first leg and the second leg only. Please do not use going to the third leg, because by the time you go to the third leg, there is so much beam spread that you will have a loss of the signal and increase in the noise, so reduction in the signal to noise ratio. So just limit the inspection to the first leg and the second leg. The first leg will actually inspect the bottom 1/3 of the weld, and the second leg, which is the sound going from here getting reflected up to here, which will inspect the top area of the weld. Next step is very straightforward. You do the range calibration. So depending on the thickness of the weld, we will set up the range. And in this case, we are trying to set up the range, a 5-inch range, and we are using a IIW block, which has two radii cuts at 2-inch and 4-inch, and you can see the signal here at 2-inch and 4-inch. So this is a 5-inch screen, which means it's 0 is here, 1 here, 2, 3, 4, and 5 here. Once the range calibration is done, then the next step is do the sensitivity calibration. This is a very important step. And the sensitivity calibration depends on what code you're using. So for piping, we generally use notches to set up the sensitivity, and these notches will be 10% of the thickness of the pipe. If we are doing pressure vessels, then we would be using side drill holes to set up the sensitivity. So that's what we do. And then we actually create what's called a distance amplitude correction curve. What is a distance amplitude correction curve? Is to compensate for the beam spread. And here you can see that we are setting up the sensitivity on the side drill holes, and these all are actually the same size holes. For example, these could be 3 millimeter diameter holes, and you can see that the amplitude, the reflected amplitude of 1, 2, and 3 is not the same. The signal amplitude drops, and this drop is primarily because of the beam spread. And in order to compensate for this drop, what we do is we connect these points, and we call this as the distance amplitude correction curve. So this is the same sensitivity line. Now, if the signal which we are actually, when we are doing the inspection, is half of this line, we call it 50% DAC. If it touches the line, we will call it 100% DAC. Now, in addition to the DAC, in some instruments, what we can do is we can actually apply a time corrected gain, and in that case, it will push these signals or pull them up, all of them to the same level. So this is called the TCG, time corrected gain. And in this case, we will apply a higher gain to 2 and even a higher gain to signal number 3, so that all of them have the same amplitude. TCG is commonly used for automated UT inspections. DAC is used for manual UT inspections. Now here is what's called the scan plan, and the scan plan is created to assure that we have full weld coverage. So here you can see we are doing, at this position, we are doing the inspection in the first leg, and in the first leg we will be inspecting the bottom half of the weld, including the root. And in the second leg, the probe is here. So basically the sound comes here, and it reflects from the ID back into the weld, and we are going to be inspecting the top half. Another thing you can actually see from this figure is that we are not inspecting from one side only. We have to inspect from both sides of the weld, which is very important. Otherwise, you will miss some areas of the weld as far as the flaws are concerned. So when we are doing the scanning, we actually put the probe here, and we can go back and forth. So we can cover the whole thing, the first leg as well as the second leg. So again, first leg from here to there, second leg coming first here and then going back into the weld. And this leg going back into the weld is called the second leg. Once we have performed the scan, we will start seeing some indications, and then after we see the indication on the screen, we have to actually locate them in the weld. And the same thing, the location is done using the RA and the DA. And after that, we have to characterize the indication. Characterization means we have to find out whether the indication is a slack, porosity, lack of fusion, or incomplete penetration, or a crack. So that depends on the location of the indication. If the indication is inside the weld, for example here inside the weld volume, most likely it will be slag or porosity. If the indication is on the bevel, most likely it will be incomplete fusion. If it's close to this location here next to the root, it's going to be a root crack. If we see it in the second leg, the sound goes here and it goes here and it's here, then it's a toe crack. So depending on the location of the indication, we can identify the indication and characterize it. So again, cracks are on the weld toe root, slag porosity inside the weld volume, incomplete fusion on the weld bevel, incomplete penetration in the root. And once we locate the indication, then we will call it a discontinuity, because then we are sure that there is actually, this is a discontinuity inside the weld area. And then we measure the amplitude and the length of the indication. So the amplitude has to be measured relative to the distance amplitude curve. And now let's go back to the distance amplitude curve. And here, if the indication is actually, let's say here, for example, the signal is up to here, then we'll call it, it's about 70% of the DAC. Okay, so once we have 70, let's say the signal is here. So this signal is 70% of the DAC. DAC is here. Now, if there was another signal which is the same amplitude here, then this signal is not 70% DAC. This is actually more than 100% DAC, because this is a DAC line. So this will be about 120% of the DAC. So then we measure the amplitude relative to the distance amplitude curve. And so that's what we do, measuring the amplitude, and then we measure the length as per the code instructions, whether we use 6 dB drop or we use the 30% of the evaluation level, depending on the code, which is in ISO. So then the last step is to apply the acceptance criteria. So knowing the amplitude and the length, we will apply the acceptance criteria. For piping, it will be ASME B311, 313 or API 1104. And for pressure vessel, again, section 8, division 1. For offshore, it will be DNV OSF 101, and structural is D1.1. Now there is many additional standards also, which are written by ISO, and those will also, they are also applicable for weld inspection. So you have to look for those. And then the last step is, this is actually the conventional acceptance criteria. Then in ultrasonic testing, we also have what's called the alternate acceptance criteria, which are based on fracture mechanics. And in this case, we have to do the sizing of the indication, which would mean height sizing and length sizing. And based on the height and the length, we apply the fracture mechanics based acceptance criteria for flaw acceptance. Now that kind of gives you a summary of the ultrasonic weld inspection, and there is a lot more to it. So if you have more interest, you have these some of my references you can read for further reading, and most of them are actually, you can find them on ndt.net also. So again, thanks for your attention, and this is a little long presentation, but I hope you liked it, and we will continue adding more and more videos and presentation to help everybody. And thanks again for your attention, and I will leave a few seconds open in case we have to add some more information to this presentation. Thank you.